Good afternoon, and I'm delighted to welcome you to today's Montgomery lecture by Nobel Prize recipient, poet, and playwright, Dr. Roald Hoffman. The Montgomery Fellowship Program, now beginning its 32nd year, is made possible through the generosity of the late Kenneth Montgomery, Dartmouth class of 1925, and his wife, Harle, who created the endowment so that Dartmouth could bring outstanding individuals to campus. Since the 1970s, Montgomery Fellows have been engaging our students, faculty, and the entire Dartmouth community. Today's fellow, Dr. Roald Hoffman, received the Nobel Prize in Chemistry in 1981, and his success in literature as poet, essayist, and playwright has touched many of us for whom the orbital patterns of electrons and molecular bonds are not necessarily dinner-time conversation. He has combined the best of the scientific and humanist minds into a single, articulate, and ever-wise persona. Professor Hoffman was born in Zwickau, Poland in 1937, a time and a place that guaranteed World War II would change his life. Not yet 4, he was moved with his family to a ghetto and then to a labor camp. Smuggled out of the camp, he and his mother were hidden in a schoolhouse attic for 14 months. His father, who had remained behind, was executed. Freed in 1944, he and his mother eventually moved to Krakow, where he first entered school. 5 years later, he came to America, where he quickly learned English, which was by then his 6th language. After receiving his undergraduate degree from Columbia in chemistry, but only after nearly switching to art history, Professor Hoffman did his graduate work at Harvard. During that time, he attended a summer school outside Stockholm, where he met Eva Borisson, who soon became his wife. The two then spent 9 months at Moscow University, where Professor Hoffman was a participant in the graduate student exchange between Russia and the US. Following the receipt of his doctorate in 1962, he accepted an appointment to Harvard's Society of Fellows, and during the next 3 years, his interest evolved from theory to working on applied theory, specifically organic chemistry. While still a fellow, his collaboration with Robert Woodward at Harvard began the research that would lead him to the Nobel Prize, which he shared with Kenichi Fukui for their conceptual advancement of theoretical organic chemistry and for the investigations into the mechanisms of chemical reactions. In 1965, Dr. Hoffman joined the faculty of Cornell University, where he has taught and performed research in organic, inorganic, and solid-state chemistry, and where he is now the Frank H.T. Rhodes Professor of Humane Letters Emeritus. From his first introduction to poetry at Columbia, Roald Hoffman has maintained a vibrant interest in literature. He started writing poetry in the mid-70s, and several books of poems have followed. If the titles sometimes tell you that a scientist is behind these works, he has one titled Theoretical Chemistry, which is probably not something that Coleridge would have used. The content lets you know that these are the works of a genuine poet. And while I typically would not read a poem by a Nobel laureate in chemistry, I think since Professor Hoffman is such a unique individual, I thought that this time probably I would do so. This is a poem that he wrote, or at least was published in 2002, if I'm not mistaken. And I believe it describes an imagined visit back to his hometown with his mother. His hometown, again, he was born in Poland. That town was actually part of the Austro-Hungarian Empire back when his parents were born. Later it was incorporated into the Soviet Union. Today it is part of an independent Ukraine. And that last detail is important for the poem. Its title is Flat Stones Beg to be Recycled. We go back, my mother and I, back to Zwickau, where Ukrainian girls in red and black embroidery sing a song, offer us bread and salt, for we are guests in their town, aren't we? But we look down, clement June turns into December, snow begins to fall, outline the scratches in the paving stones so they grow into Hebrew letters. We stand in a minefield. My mother has trouble seeing in the snow. In addition to his poetry, Professor Hoffman, as I said, has been an essayist and has also written a number of plays. Included among those is a play that he co-authored with Carl Gerasi called Oxygen, which deals with the discovery of oxygen and the importance of the scientific process. In order to bring his love of chemistry to the general public, Dr. Hoffman starred in the World of Chemistry TV series. He has also been a host of a monthly series at New York City's Cornelia Street Cafe called Entertaining Science. A fellow of the American Academy of Arts and Sciences and of the American Philosophical Society, he has been much honored by his colleagues. He's the only person to have received the American Chemical Society's awards in 3 subfields of chemistry: the A.C. Cope Award in Organic Chemistry, shared with Robert Woodward, the Inorganic Chemistry Award, and the Pimentel Award in Chemical Education. In 1983, he was given the President's National Medal of Science, and many other distinguished awards and honors have been bestowed upon him. Describing the bridge and bond between science and literature, Dr. Hoffman has remarked, "The language of science is a language under stress. Words are being made to describe things that seem indescribable in words, equations, chemical structures, and so forth. Words do not, cannot, mean all that they stand for, yet they are all we have to describe experience. By being a natural language under tension, the language of science is inherently poetic. There is metaphor aplenty in science. Emotions emerge, shaped as states of matter, and more interestingly, matter acts out what goes on in the soul." It is a great pleasure for me to welcome Roald Hoffman to Dartmouth. It is as both a scientist and a poet that he speaks to us today in his Montgomery lecture on the subject of chemistry's essential tension.
Okay. Thank you very much. I am very grateful to the Montgomery Endowment for giving me 2 weeks in which I can live out my life, which means do the science and to teach. I'm now retired at Cornell, but still active in research, and here I am in a few classes, and it's nice. And also to do some things connected with the arts. One of my plays was staged, thanks to Peter Hackett and his crew, and it was beautifully done last week, Wednesday, and that was wonderful. So I want to tell you about chemistry, a task. We're going to do this in and I want to convince you that chemistry is interesting. Let's see how that works. We're going to do that by taking 3 views of chemistry and then say something in conclusion. The first view of chemistry is one that preceded the existence of chemistry by hundreds, if not thousands of years. And that is that chemistry is the art, craft, and business, before there ever was a science, of substances and their transformations, things and things changing. Now, the reason that this is an old definition is that people were changing things. We've been put on earth to do that for millennia, whether it is in extracting metals from their ores, or in cooking, or in cosmetics, dyes, textile preparation of various kinds, soaps, and all kinds of transformations of matter in one way or another. These are of great interest to me, and I talked in a way about one of these in a lecture last week about indigo, a dye. But I need to sort of perhaps give you an example of a transformation of this definition. And so I did not know if the safety committee of this hall would allow me to blow something up. And so I brought some slides. So here are 2 substances. One is a beaker with a liquid brownish red and a gas above it of bromine, the other one aluminum. On the right, 2 elements which were available in pure form only about 200 years ago. Aluminum was very precious in the first decades of its existence. It was made by Humphrey Davy, or rather by someone else, but it was so precious that Napoleon III had a dinner service of aluminum which he served his best guests on, and the second-rate guests ate on gold. The tip of the Washington Monument was made of aluminum. Within 3 years of the construction of Washington Monument, 2 young men, one at Oberlin College, the other one in France, invented a process which makes aluminum as cheaply as it is today. Anyway, one is placed into the other. There are flames, smoke, foul odors, absolutely everything you expected of chemistry. And at the end, there's something else, something fundamentally different. This is chemistry. This was chemistry. To this day, this remains what interests young people about chemistry. If you want a description by someone outside the trade, you can look at Oliver Sacks' Uncle Tungsten, Memories of a Chemical Boyhood, and he was here as a Montgomery lecturer, for an account of the excitement these simple transformations cause. Now, the transformations need not be with such wasteful release of energy, as nice as it is here. They can be slow. I took this picture of a Japanese breakfast I had, and not here, but in Japan. And the chemistry that went into making the fish or the pickles, the vegetables, the biochemistry that was behind these is slow on the scale of things, or very fast, except we can't see how fast it is. And you can be sure also that the chemistry we normally associate with chemistry, the chemistry done in a laboratory here at left, or in a big chemical factory or refinery, that chemistry is not done in the way that aluminum and bromine reacted with each other. It's done in ways to economize on energy and on the atoms being transformed. But this still remains a kind of image of chemistry, of a fundamental transformation, sometimes violent, and it leads to something in public conceptions of chemistry. So here is a 1942 Donald Duck comic book. Carl Barks, one of the original members of the Walt Disney stable, wrote the whole book and illustrated the whole comic book. Today it would take 200 people to do that with modern computer animation. Here is, you can't read this, but you don't need to read it. There are ritual things going on in Donald Duck comics. Donald Duck comes in, the nephews are doing something, Donald Duck does something stupid. No one's wearing safety glasses. There is an explosion. There is the obligatory egg on a head over here. What's interesting is that you can't see it, but there's a lot of chemical words here, like, so what if benzene is misspelled? It's pretty close. The really most interesting thing here is the next panel on the Donald Duck strip, which I've enlarged, where he says, as you can see, if I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen, and the nephews answer appropriately. The point is, or one interesting thing is, that this reaction has not been run to this day. And you have to grab a chemist and ask them why it's difficult to react CH2 with NH4, both neutral. So that's... Anyway, why do I show you this to you? Because it's fun, of course, but also because this is part of the public image of chemistry. Chemists are the people who make things go bang, okay? So, and that is going to be part of the third thing that I'll talk about, third view of chemistry, and that is in perceptions of chemistry, but it already comes up here. There is another interesting interaction or outcome of that very first definition of chemistry, that it's things and things changing. And it was something historical, and it's interesting to probe this. So when there arose across cultures, in China, India, in Egypt, then in Europe, philosophies of transformation, the philosophies being often drawn from the same myths that powered the religion around them, but often in some conflict with the religion. The myths, let me just say right away that to me myth is a good word, okay? So what I'm talking about is the myth of Persephone returning from the dead, of Phoenix rising from the ashes, or the myth of the resurrection. All of these wonderful renewal things or new creations, these were philosophies of transformation, basic transformation. Of course, desired transformation from a sick person to a healthy one, from a poor person to a rich one through the making of gold, the vain hope of immortality. Many Chinese emperors died under the influence of their alchemists. So I'm talking about alchemy here. These are some of the images you see. Alchemy draws very close to the psyche in a number of ways. Jung had a great collection of alchemical drawings. We're going to see soon a new Jung book out. Let me give you an image which illustrates what alchemy was. So when there arose these philosophies of transformation, and they were hermetic in some way, secretive, which is the way things are, and they were sometimes complicated, and when they needed, this is not a conventional view of alchemy, but when they needed something to get into people's minds with, a logo, a symbol, they chose chemistry. And because chemistry already, before there were ever chemists, was seen as transformation, as being symbolic of transformation. You heated up mercury and you formed a red crust on it. And you heated up that red crust and it went back to mercury. I mean, those are magical images of transformation which capture the public imagination. Here's a typical late alchemical image. As I told you, this is not a typical image, this is not a typical view of chemistry. The usual view of chemistry is, by scientists, for instance, is they take the chemistry the alchemists did. They, after all, did derive they did for the first time make the strong mineral acids, hydrochloric, sulfuric, hydrochloric, and people ignore the philosophy that underlay it, and they laugh, chuckle a little nervously at the charlatanry that inevitably accompanied something like the transformation of lead into gold, let's say. Well, here's a typical chemical image, and it grasps right away the interesting thing that's happening. In the back, a king and a queen are getting married by a pope, and in front people are doing some chemistry, and in recognizable images. Now, it was given to me in the 60s to go to a number of hippie weddings in California, and I saw some chemistry being done, but it wasn't this kind of chemistry, okay? So what's happening here is something on a symbolic plane. The marriage in back has something to do with the meeting of the elements, the chemical wedding, as it was called, of what's happening in front. Alchemy is very interesting. It captures the imagination of psychologists and of artists. There are just two things to say about alchemy that I want to leave you. One is not my own, but that of Mircea Eliade, a philosopher, historian of religion. Eliade had something thoughtful to say about alchemy. He said that modern chemists, crying all the way that they had nothing in the world to do with alchemy, they were scientists, have succeeded in accomplishing exactly what the alchemists set out to do. What he meant was not to turn lead into gold, but the lead is what Merck Sharp and Dome starts its synthesis of pharmaceuticals with, and the gold is what we pay for it, okay? And along the way, healing takes place, real healing. So in that sense. The other thing I would say is that there is something about alchemy that's very interesting because it captured the public imagination as well as the private imagination among intellectuals and other people in Renaissance Europe, for instance. And here we are today, modern chemists, able to do transformations which the alchemists only dreamed of. And we have trouble capturing the public imagination with the skill and power of our transformations. We desperately need something like alchemy. And it's a real challenge. Oh, this is a late alchemical painting. You see it's dated 1570, Jan van der Straat. You can see this in Palazzo Vecchio in Florence if you go. It's a large painting. So the Duke of Florence, I forget which one now, was, maybe somebody remembers who it was in 1570. He's here in the yellow vest here, seemingly making an omelet. He had commissioned his new alchemical cum chemical laboratory somewhere in between, and so he commissioned this painting, and it's a nice court painting. A lot of interesting things about it. The beautiful androgynous figure in the middle is Bianca Capello, then his mistress, and later his second wife. Anyway, this is the reason I show this to you. This is the first illustration out there in art of the sociology of scientific research. Here is the master alchemist wearing spectacles, which was very expensive at that time. And you notice he's doing nothing. He's just pointing to people, telling them what to do. And so that's the professor. And all around are the people doing the work. That's the graduate students. Okay, and there's even somebody up there, it's cut off, up at the top there, who is actually writing things down, taking laboratory notes in a little scriptorium there. Anyway, I think alchemy was a fascinating historical interaction of chemistry and culture. The charlatanry aside, it's extremely interesting as that, and a rather unique occurrence in the history of humanity. Okay, that's the end of the first definition of chemistry. The second definition of chemistry, it comes this way, that over the last 200 years especially, and without waiting for any microscopes, despite IBM propaganda, that to show us what is inside matter, through the hard, hot and cool work of our mind and hands combined, we learned that inside those substances undergoing transformations, there were, on the microscopic scale, molecules, atoms, yes, but much more interesting than atoms, groups of atoms called molecules, which persisted, and those, and so now there is another microscopic definition of chemistry, that chemistry is the art, craft, business, and now science of molecules and their transformations. And these two definitions get inevitably mixed up in the minds and language of chemists as they talk about what they do. They manipulate macroscopic compounds, but they talk as if they're manipulating molecules. Well, they are at some level, but the two languages get mixed up, and the motion between them it influences the language. It's very interesting. Here are some examples of some molecules that are simple and beautiful. So there's a tetrahedron of 4 carbons, and then around it 4 hydrogens, a cube of 8 carbons, a dodecahedron on 20, and finally a molecule, Marcelo, that should be on a flag of Brazil, right? So the Buckminster fullerene over here. So these are simply beautiful, beautifully simple, and devilishly hard to make. Not the last one, actually. And there's something interesting for the young people in the audience. And that is that of these molecules, I'm just going to say it, but then I would like you to think about what it means. These molecules were made chronologically by human beings at a certain time. I could tell you who first made one of these. Doesn't matter. But they were made chronologically. And the last one to have been made in the laboratory, which is the Buckminster fullerene of these, is the easiest to make. And just think about what that means for the future, or for what can be out there. Okay, now these molecules, these models, static models, ball and stick models, they're not really olive stuck through with toothpicks. They're really vibrating and alive in various ways. But they are, you see them, they give some representation, some iconic representation of what these things look like, much enlarged. And when I see these, I feel guilty. And let me tell you why. The reason was hidden in that beautifully simple statement. So I'm going to go off in a little excursus on simplicity and complexity. The thing is that I don't have to tell you that these molecules are beautiful. They've got a beeline into our soul. They're Platonic polyhedra. So the thing is that I know there are other molecules. Here is one of them. This is probably the last time, not quite, because we now have 3D printers, but this was actually a physical model built between 3D printers of a protein with all the 9,500 atoms in it. About 4,500 hydrogens, about 2,500 carbons, 700 nitrogens, 700 oxygens, 12 sulfurs, and 4 irons. It looks like a holy mess. This is an attempt to reduce the complexity by stripping away all the hydrogens, and a representation which focuses, the slide is not too good, on the backbone of the extended chain, so-called biopolymer that is underneath this. And this still looks like a clump of pasta congealed from primordial soup, like a tapeworm quadrille. There is nothing simple about this. There is nothing simple about this. And I had to learn to love this molecule. I had to take someone by the hand, or force me, in a course, either one. This is the biochemical molecule that we know more about than any other biochemical molecule in the world. This is hemoglobin, the oxygen carrier in our blood. And the carrying of the oxygen takes place through the 4 iron atoms in these little platelets that you see nestled, 4 of them. There are 4 so-called subunits that are nestled in the arms of the protein. And so where is chemistry? Well, biochemistry is definitely at this level of complexity, but where is chemistry? Is it here or is it there? It's somewhere in between in general, and probably closer to hemoglobin than it is to that. And the point is that this is not beautifully simple. It is learned beautiful, or something. It actually fits in with nice Kantian ideas about beauty. We'll come back to that in a little while. But I want to talk a little bit about this in another context. If you take these molecules, these are nanoscience before the buzzword was invented. This molecule is 5 nanometers across, 50 angstroms across. And this beautiful structure is quite remarkable in a number of ways. A little change is what causes sickle cell anemia and other things like that we know about molecules. If you go, well, these things are obviously structures. They have a shape, very prominent here, but they even have a shape here. They're structural elements which we combine into a story about the molecule. The shapes are interesting, and there is a kind of architectonic feeling about this. And they actually can be made in a laboratory. Molecules as complex as this can be made in interesting ways. The making of molecules is another story, is not quite like the building of a house, but it has some elements in common construction principles with it. It's an interesting kind of building. But once you see that these are architectural, if you start to think then, what if I go upscale? If I go, for instance, 12 orders of magnitude, 12 powers of 10 upscale from this scale of 5 times 10 to the minus 8 centimeters, 5 times 10 to the minus 10 meters, then I reach the scale of this building, or I reach in general the scale of, let us say, architecture or monumental architecture, another kind of building. And what's interesting is that the same questions of simplicity and complexity are played out in our views of buildings as were played out in my talking about simple and complex here. So here is an example. I could have shown you the Parthenon in Greece, but this is the Taj Mahal, a high point of Islamic architecture. And you see clearly the bilateral symmetry. This is the ideal of simplicity being played out here in an architectural building. Let's go somewhere else. This is in Bavaria, the Wieskirche. Outside is symmetrical. We'll go inside of it because it's built by human beings. But take note of the nature around. Is nature ever symmetrical? Is what we like about a mountain that one side of it look exactly like the other side? Part of Fuji, yes, but not in general. Nature is what it is, but it's not symmetrical. We go inside the building, and we are in another aesthetic from the Taj Mahal. There are straight lines, yes, but if any line can be made curved, it will be. This is the Baroque, the Rococo, and the aesthetic is different here. Somewhere else, this is the Transparente in Toledo on the left, incredible complexity of sculptural structures going up through there. This is a temple in Madurai in South India. This is the gatehouse of Park Güell, a structure that looks different from every angle that you look at, exactly 100 years old, of Antonio Gaudi. And so this is complexity, so there's the struggle between simplicity and complexity. I think there is, let's see, let me say something. I think simplicity and complexity are two parts of a contending aesthetic to which we'll come back to. By and large, I would like to make a case for complexity. What worries me about simplicity, let me put it another way. I think simplicity, I think there are psychobiological reasons why we favor simplicity. If there were a tiger coming in through that door, please don't look, there's no tiger. But if there were one, I don't have time to process that cognitively when I see the stripes and say, what the heck is a tiger doing in Filene? And is that a zebra or a tiger? I have a tenth of a second to start running. And that was learned early on. So what's coming in through the senses is too much information. We have to reduce it. We have to simplify it. That's, I think, behind our simplicity. The thing is that it's universal and human, and that scientists who think sometimes they're smarter than other people, crazy, but they are as much subject to this as other people. Simplicity is behind racial stereotyping and all kinds of other bad things in this world. And scientists, so where does it come up in science? It comes up in physicists who think that equations must be right because they're pretty. It comes up in chemists who think that cubane is beautiful and that I had to struggle to learn what hemoglobin is. And if I give someone the choice between two mechanisms, one of the mechanism being a sequence of reactions explaining something, one mechanism that has two steps in it, and the other one that looks like a Rube Goldberg device with 3,941 steps, you can be sure I made a good living of the first one, the one that takes one step, as Dave knows in this. But if you give people a choice, there are inherent prejudices for simplicity. And I think, given that, we have to be watchful. Given that our mind is pushing for simplicity, we have to favor the opposite in some way, or find ways to introduce the opposite. But maybe I've got to end this tirade against simplicity. So let me try to repair it by going further up in Park Güell. Here is the plaza. There's a courtyard here. It falls off here. And benches had to be made by Gaudi with help from another architect, Joel, and mosaics. And to me, I'd like to look at this. So where does beauty resides? What makes this beautiful? You notice that there is regularity in the benches. This particular view of the benches emphasizes the regularity. Note, incidentally, that it's a curved line. Curved lines are inherently more interesting than straight lines, despite scientists always trying to find straight lines. Curved lines are much more interesting. I'm not going to go into the psychology of that. But the other thing is, look at the mosaic here. What is going on here is that, or imagine another possible design where there were black and white square diamonds or diamond shapes. It wouldn't be as interesting, as beautiful as this one. So what is it here? It's that some of these things are regular and some things are irregular. And there's an artist's innate ability in the color sense that they bring to this, what colors go with others or contrast. So where does beauty reside? Beauty resides not in simplicity or in chaos. It resides at the tense edge of order and disorder, of simplicity and complexity contending in our mind. That's what makes this structure interesting and beautiful, is that we keep moving between the two. Immanuel Kant would have said it, that the beauty is to be found in a simultaneous contemplation, he would say disinterested contemplation of this object, engaging both the imagination and cognition in the viewing of this object. That is, there is an innate reaction and there is also a thinking about it. And both are important in these aesthetic judgments. Let's see. Maybe I have time for this very quickly. By now you've forgotten where we were because I went off into this tirade. So where we were was the second definition of chemistry, that it's molecules and their transformations. And so I want to tell you, and I showed you pictures of molecules. I didn't show you anything about transformation, and I won't, but I'll just sketch something. It's an interesting thing. Here is a molecule, a diatomic molecule of iodine and chlorine, iodine monochloride or chlorine monoiodide. And this is Richard Zare, a wonderful chemical physicist, physical chemist at Stanford. This is his work. He shines a beam of light on this, and he's not living too far from the Disney studios, so there's a cartoon here he's drawn. And the light comes, and the two electrons that make up the chemical bond, there's a zap, and the bond is broken by the energy of the light, and an iodine goes one way and the chlorine goes off the other way. And that looks very simple, except each goes off with one electron in a bond. And now there's something interesting, because they actually look at the chlorine experimentally. This is an experiment. They look at the chlorine, and the thing is that the thing is sailing in a certain direction, and I'm desperately trying not to say orbital angular momentum, but the electron is moving around this, and it can move in a direction on top, which you call topspin, or it can move in a direction opposite to the direction which it's moving, which is backspin. Does it make a difference? Oh, in the macroscopic world, it makes a difference. If you're a tennis or a ping pong player, boy, you have a tenth of a second to adjust your racket if you perceive that impact or from what the opponent does, that it's going with topspin or backspin, to otherwise the ball will go over you or under you. So if, to the extent that chemistry is classical, like tennis balls and ping pong balls, you can tell the difference. And he devised an experiment to tell the difference between the two. But then he found something really strange, And this is that when he changed the energy of the light, which he shone in order to break the bond, and increased its energy beyond the minimum that is necessary to break the bond. If the chlorines went off with topspin initially, they started going off with backspin. And then he increased the energy some more. That means shifting the light to the ultraviolet. And they started going with topspin. Bizarre. And it's as if the energy of the light was tuning whether it was topspin or backspin. Now, what this has to do is with quantum mechanics. I cannot give you an explanation of this. Classically, it involves some quantum mechanics, and the chemistry is somewhere. That's what chemistry is interesting and difficult sometimes, is it's moving between the classical and the quantum mechanical world. In the world of structures that you saw, it's very classical, and a lot of chemistry, organic and inorganic, is like that. But any time that light is involved, then the quantum view has to come into view. They investigated this using quanta of light, using lasers with light, very monochromatic. This painting and the next one by Giacomo Balla, Italian futurists were obsessed with motion, and this is very interesting to see that their ideas. Why do I show this to you? Because the stroboscopic capture of the motion of the dog here, or the lady's dress in this wonderful picture by Giacomo Balla, is actually what we can do today for molecules. But in order to capture molecules that are moving at the speed of sound through this room, that's what oxygen and nitrogen molecules are doing, to capture them this way, we need pulses of light, which are 1 million billionth of a second long. And we can do that today. There is a chemistry to do that. It's a very exciting time for capturing actually the motions of molecules. But now I want to go to the third view. And this third view is in terms now, so the first ones were substances and their transformations. The second one was microscopic molecules and their transformations. Now let's talk about perceptions. People do not live by bread alone. What do people think of chemistry? This can be, I already gave you a piece of that in a Donald Duck cartoon. That's part of what people, but this is something I got. It's a complicated slide. I'll explain it. Supposing someone in I was asked to testify in Congress, and they gave me 10 minutes to tell them what is good about chemistry. They're not going to do that. They want, depending on what the senators are interested in, they want to know what's bad about one particular thing. But supposing that were happen, ideal world, I am not a politician, but I'm not stupid. I know I will choose an example as close to health as possible. So I went to a doctor friend and I said, show me something about what chemistry has done for a thing. And this is a plot, this is a plot of, there's a time scale here. And here this is for tumors of this is surviving 5 years after diagnosis for children with 8 kinds of tumors. There's a reason I didn't become a doctor, so I don't know what rhabdomyosarcoma is, but it doesn't matter. I know what some of these things are. The tumors of children, in exception of brain tumors, are generally different. They're developmental rather than of the surfaces of our body. But turns out that that after accidents in developed countries, that tumors are the next killer of children. And we don't hear much about this. And the time axis here, time axis is interesting. This is from a medical journal. You notice it's a certain interval here for 10 years, here for 15, here for 20. It's neither linear nor logarithmic. I didn't know you could do this kind of thing, but in medicine you can do this kind of thing. Aside from the dates here, there is little blocks in this complex diagram for certain techniques. Surgery comes here, Radiotherapy, despite Madame Curie, there was not a large availability of radioisotopes till the atomic bomb work. And so this turns on at the time of World War II here for radiotherapy. And then, of course, chemotherapy, conventional and intensive. And what you see briefly is, this is what I would say to the congressman, except I really wouldn't. This is too complicated. Them. Nothing happens until chemotherapy begins. And then eventually you have 6 of the 8 tumors. You have a chemotherapy working from 75 to 95% of the time. And for 2 of the tumors, something is waiting for the young people in the audience to find. So this is integrated 200,000 children's lives saved. So that is my good statement. That's my good chemistry slide. It took a little while to explain and too complicated. But it does show the utility of chemistry. I know it's medicine too, but I'll take all the credit for the chemistry in this. The problem is out of the back doors of the same companies making these materials for chemotherapy regimes. And it's maybe not the same companies. It's always some other companies. These companies that are making the chemotherapy are under public purview. But coming out of their back doors is this, which is not anything specific, but is a slide, emblematic slide to illustrate the infinity of ways which we have found to foul our own nest. And so this is the benefit first and the harm of chemistry coming here. It sometimes is all in the same molecule. I want to make that point that there's no escaping this. I mean, here's morphine. There's a chemical formula here. It may be the first chemical formula here, simplified, and at the left is a bottle of morphine. So anyone here who has had an operation knows what morphine is good for. And morphine is and a derivative of it, heroin, is a deadly addictive drug. And, it's not a different molecule. It's one and the same molecule. The same for the ozone, up there protecting us from the ultraviolet, down at sea level, the product of photochemical smog in Mexico City ruining tires and lungs. It's not any different molecule. It's one and the same molecule. Chemistry is truly the anthropic science. Those galaxies and quarks are intellectually interesting, but they can't heal you nor hurt you directly. Molecules can do that, both of those things. And that gives rise to this one of the tensions and one of this two-faced Janus image of benefit and harm, but emblematic in turn of a number of tensions in chemistry. And there are a number of things to say about this. About harm and benefit. Just as long as I'm here, I'll come to the tensions in a moment. Let's see. Some of my colleagues think there is a cabal out there in the press to make the word toxic inseparable from the word chemical, so that the two go together always. There is no cabal out there. The press is the press. Good news is no news, bad news is good news. It always has been that way. I lived for a year, and Barry was also in the same exchange in the Soviet Union that I was, for a year in a country in 1960 where never a bad word was said about the chemical industry of that country. I don't want to live there again. That's the only conditions under which you'll get all good things said about chemistry. The second thing is, because it's truly on the level and can hurt you and heal you, and when you go to see a doctor and you want an antibiotic, you want it to heal your child, and you are worried about it, the side effects of it. Because there is set up, because of this hurting and healing, there is set up a bond between human beings and molecules. Why can they hurt you or heal you? Because they interact with other molecules in our bodies. So there's a time to take advantage of this in a class, and everyone should go out in a chemistry course and look at the New York Times in the morning, and it'll never give a chemical structure. That's much too much for the readers. But thank God it gives once in a while the name of the molecule, and with the help of Wikipedia or Wolfram Alpha, you can get the structure of the molecule in 5 seconds and put it on a slide and show it to your students, and do this every day. And slowly people will build up the feeling that the changes matter, and that the difference between the male and the female sex hormone is just 2 atoms for 2 of the, and the difference between methamphetamine and the decongestant from which it can be made is 1 atom. And it's easy kitchen chemistry is what gives us troubles. There are so many meth labs. All of this can be gotten. The last thing I would say about good feelings about chemistry, sure, we'd like people to feel good about chemistry, but I think there is a psychological reason why people will never feel unambivalent about chemistry. That's a double negative. Why people will always feel ambivalent about chemistry. It's because chemistry, as I've showed you, is deeply and fundamentally about change. And if you think about how people feel about change in general in their lives, we have ambivalence. Governments would like change to increase commerce, innovation and commerce, but by and large they're as conservative as can be. God forbid we should amend the Constitution of the United States. It takes great efforts. But people individually, yes, when in those days when my children played the same stereo system, now thank God they have earbuds, then you could listen to their song 10 times before you wanted to turn it off. But we want something else after a while. But if you think about deeper things, like do you want to change your relationship, a job, the place you live, we're a little ambiguous about change. Given that we're ambiguous about change, I see no way in the world, this calls up the alchemy story again, there is no way in the world that we will feel unambiguous about something so emblematic of change as chemistry is. It's really about change. And if we're ambiguous about change, we're going to feel ambiguous about chemistry. Why do I have this slide here? Yes, I was going to move to another tension. And so this is, these are plants of the allium family. Where would the world be without them? This was just to prompt me to talk about natural, unnatural, another tension within chemistry. So what's natural about this? Obviously it looks natural. Yes, a few garlic plants are natural, but 1,000 acres of garlic is not natural. It's agriculture. And agriculture is a human activity using live organisms. Now, natural, unnatural is very, very ambiguous. What's natural about a poem or music or many of the things? There are good things about natural, but we could talk some more about it. I could tell you, I would like you to think about it. At the back of cotton, rayon, and nylon, somewhere back before those were made, there is a plant and a seed. In back of all of those. Nylon is obviously synthetic. Cotton, we think, is natural, except for agriculture. And rayon, most of us don't know what rayon is. But rayon turns out to be not that far from cotton, just treated a little bit. Anyway, the plant that gave rise to those things, which plant is truly natural in the sense of never having been touched by a human being? I'll leave that. What I want to get at is the title of this talk, which is Chemistry's Essential Tensions. And there was a plural there I put in, but there is one tension I'll talk about. So what I've done with you is, using a number of examples, I've talked about some of sort of polarities or dualities. This is a very Jungian approach to chemistry, but I never tell that to my colleagues because they'll get scared. So I've talked about macro, micro, simple, complex, symmetry, asymmetry, harm, benefit for sure. Everything poised on these axes, possible of being used by human beings, possible to be both often, as the morphine molecule, natural, unnatural. There are a number of other tensions. One of the most interesting ones is synthesis and analysis, or creation discovery, because chemistry in the 20th century on is the art and craft of making molecules, and often ones that did not exist on Earth before, though some that did. And that makes us creators with all the ethical responsibilities that some of us would like to avoid that come from creating things, whether it is a child or a molecule or a gun. What's interesting about this is that the philosophy of science in general was not made by people who are chemists, and so the general aspects of thinking about science are based on ideas of science as discovery. And the logic of creation engenders its own questions and its own ways of thinking. It puts chemistry, because chemists are the makers of molecules, in some ways close to the arts. Lest we get too high on that, it also puts us close to engineering, people who make bridges that shouldn't fall down. Okay, so it's somewhere in between. We could talk about the reveal to conceal. What do I mean by that? I mean, when I discover something or create a new molecule, do I patent it or publish it? Part of this here. Trust skepticism. But I actually just want to mention the last one, the same and not the same. This is, I'll put it, if I can, this way. Here are 4 white crystalline solids. One is sugar, one is salt, one is tetrodotoxin, a neurotoxin from the pufferfish from Fugu, and the fourth one is penicillin. I've actually forgotten which one is which, but it doesn't matter. You were out on the table, you're asked, you're going to play chemical Russian roulette, okay? You are asked to taste these. You don't have to be a naive realist, I'm talking in a philosophical sense, to not be willing to do this. Your body knows the difference. 1 milligram of tetrodotoxin will kill you. 1 milligram, 1 crystal you can barely see. And so there are 50 million compounds that have been made. 30 million of them are white crystalline solids. Okay, so the question is one of identity, I put it that way, or is this the same as something else? What is it? Is it the same as something else, or is it different from something else? How does it differ on the atomic level? This is a very interesting tension in chemistry. A painting by Theodore Chasseriau. Are these twins or are they just sisters? These are some examples of the tensions, and I would like to leave with you the thought that chemistry is interesting because it is anthropic on a human level. And it's interesting because every fact in chemistry, if thought about, can be thought in terms of a number of polarities or dichotomies where things can move along an axis from one to the other. And I think that's very interesting. That's what makes chemistry interesting to me. Maybe I'm too contemplative about it, but I think some of them are so clear, like harm-benefit, which is the most obvious one that we can focus on, that it's very easy to convince people. The identity is also touches upon things in our psyche. We want to know how we are the same or not, how we differ or are similar to our siblings, to our parents, to people from another country, religion, background. I want to finish with just 4 slides that are coming, and this is something in a way to address, it's like a little epilogue. It's something addressed to the young people in the audience, but it also addresses a little bit the question, not the question, but what you've seen me do, and that is to use art to illustrate or to interact with science in these things. Now, in part, I'm playing out what I didn't get to do, that is to study art history, right? So now I'm doing it, but I'm not really being fair to art history because I'm largely in an illustrative mode, but on the art. But now I want to do something else, which you'll see, which brings the two together now with writing. So here is an icon of chemistry. Again, I didn't think this was a good chemistry room. When I gave a talk to Chem 10 yesterday, I could be sure that would be on a wall. But this is Mendeleev's periodic table, an extremely interesting object in a number of ways for what it had and didn't have in it, and how it was constructed. But that's not the point. The point is this is a masterpiece of chemistry. Made in 1867, drawn down the first time. There were precursors, refined. Less than half of these elements were there in 1867. It remains the icon of chemistry and remains extremely useful. And I work with it all the time, every day. When young people see masterpieces, there is sometimes a feeling, we have strong feelings of inadequacy. There's sometimes a feeling, how could I possibly do something like this? How could I come up with something like Mendeleev's table? So to deal with that, what we need to do, of course, is to see how Mendeleev did it. Just like in autobiography, probably what historians of science have learned is probably it's good to ask the person who did it, but take it with a grain of salt. Mendeleev did good work. He was praised with it, for it, and he told a story that he had to make the textbook, that is true, and he put the recently agreed on atomic weights of the elements, how much they weigh relative to each other, on playing cards. And then he shuffled the cards he arranged the cards in an ordered way to see similarities between different elements. So that fluorine, he sort of drew a snake, and the fluorine came above the chlorine, the bromine, and the iodine. It's a good story. He told it a number of times. It grew better each time. There is no evidence, there is no playing cards, nor the only evidence there is for his telling the story from a number of people. If you look in his notebooks, you see this. Okay, let me try to explain this. This is the earliest mention of the periodic table in Mendeleev's notebooks, thanks to some of my Russian colleagues. So the atomic weights were agreed on. The symbols are the same we have today. You see FONCB, like today. They were devised mainly by Berzelius in 1830. This is 1867. He, like any person, you're asked to order something, so you make a list of things. Not quite a shopping list, but a list of things in the way that so he makes the elements with the atomic weights written above them, a list, and as he fits them in, he crosses them out. It's like a shopping list. He's writing in a mixture of Russian and German because he studied in German Über. He says, I don't know why he writes it out this way, but 3 elements he couldn't fit in the first time. It is in the nature of theoreticians in this world to make things fit in that don't fit in. And so he made them fit in. And you look at this, you have to turn this by 90 degrees to see the modern form. That is, the nitrogen, fluorine, oxygen here is coming down, whereas here it is going over to the right over there. But it's recognizably the periodic table with the few elements. And what is the most beautiful thing about this? The most beautiful thing is the crossing out, for God's sake. This is the prima facie evidence that this is done by a human being and not by a machine. This is a human being desperately trying to understand this piece of the world. And contemporary historians of science are wondering, what have computers done to this? Who is going to save the drafts and the little jottings of paper? Okay, so this is science, and you can see that this is a human being, and I think this should be encouraging to a young person because it looks like their notebooks, okay? It looks like my notebooks. And it's very hard to convince people that that is so, but it is so. Now, human beings are so funny. They think if you show them this, evidence that that work matters in getting something, human beings still would like to believe that there is some piece of our experience where perspiration doesn't matter, but inspiration does. And the usual focus of this are poets. So these 19th century Gilbert and Sullivan-like poets who are walking on a beautiful fall autumn day, are walking the streets of Hanover, New Hampshire, and doing nothing the whole day long, and then at the right point whipping up a little notebook like I have, and then writing down here the poem full-blown like Athena sprung from Zeus's head. The poem, it takes shape. Well, let me show you. Here's a poem, a well-known poem in the English language, William Blake's The Tiger. Tiger, tiger, burning bright in the forests of the night, what immortal hand or eye could frame thy fearful symmetry? This is the last manuscript we know. It's still missing a stanza, but it has the printer's mark across it, so I don't understand this quite that we have. But what's interesting is it says, could frame thy fearful symmetry, but he had dare here. But dare didn't work, so he put the dare down here. He had dread grasp, it didn't work there, so he put it in there. That's a salvage job. I know exactly the feeling. You have two words which mean something more than those two words mean by themselves. You're going to get them into a poem somewhere. All right, science and art are not the same, but there are commonalities, there are differences. I think what this is, I think it should be encouraging. It is encouraging to me to see the evidence of the work, of this work. And in both of these, I think art and science are two parts of humanity. There is something like inspiration, there is perspiration too, a lot of that. There is a matter of putting pen to paper and starting, and it's amazing what one can do once one begins. I think the human condition is to create, to try to understand, and I can find no better way to show that to you than to leave you with these two slides. Thank you very much.
Maybe just a few questions, if there are any.
Oh,
and
sure.
We also have a
microphone.
Do you have a question?
Back in high school, I watched your world of chemistry videos.
Yes.
I was just wondering, to jog my memory, when those were filmed and
Yes.
kind of how you were involved in that process.
I had some more hair then, isn't that right?
Yeah, but I think, your skin hasn't aged at all.
It had. Well, thank you. Those took 2 years of my life. They were films made for Annenberg CPB with 26 half hours. There's nothing better has been made since. I still hear from high school students every week about them. They were made in the end cheaply enough that every high school in the country had them. There were 2 live people, who was supposed to be serious, and Don Showalter, who had all the fun of doing the explosions. That's what you probably remember. Took 2 years
And
of
the
my
opening
life,
theme.
and I'm very glad I did it. It was
Glad
very
I was
hard.
able to watch them too. Like,
Thank you.
I think this is on. Thanks. So Roald, you go to the science section in a bookstore and you see books on black holes and the
Yes.
Big Bang. All these physicists writing books, myself included.
That's right.
Very few chemists.
Yes.
Why is that?
There are some chemists in there. They don't seem. I think people. I think we are closer to practical and mundane in a positive sense in many of the things. And attempts to glorify polymers or other aspects run into some trouble. I don't know exactly why that is, but those things have to do with revealed mysteries, or many of the physics books seem to be there. It is, we have a dearth of good writers in chemistry. And I'm too, I don't know, I'm not centered enough to write popular books. I'm idiosyncratic in what I write about. It's been a pleasure and a good life to do so. Others, Philip Ball is probably the best, and he has some chemistry background, but he's super at describing a number of aspects of chemistry. Many of the heroic figures of chemistry did not take on popular writing, like Pauling or the person I collaborated with, Woodward, though they wrote beautifully in different ways and convincingly, very different styles. Woodward in a high style, Pauling in a direct forward American style. They did not, Pauling did do one book which was about scales of 10 essentially in the molecular world. We are not too good at writing.
Thank you. Has the excuse me, has the emphasis shifted from 50 years ago, when we had better living through chemistry, to nowadays, when a chemist isn't even called a chemist in the newspaper?
Yeah.
Looking for one, he's a material scientist.
Yeah. So, in general, chemical companies, with some exception, have shied away from a chemical work in their advertising and publicity. The other aspect about is an interesting decentering by which a field is defined by its borders with molecular biology and with material science. And we can't seem to generate the buzz within chemistry. It is something to deplore. I think the center will not go away of chemistry. It is interesting to look at how we let biochemistry get away. We'll blame the Germans for that in that case, because it happened early on in the 20th century, probably in Germany, when it was the major chemical power, so to speak, in terms of research. There is some merging together again of giving chemistry a certain role in biological processes. I am very proud of being a chemist. It took me a long time to be one. Halfway through graduate school was only when I decided to be a chemist. But I'm very happy with it. I love this in-between field. I love this fuzzy thinking and the things and this movement between really understanding things and just looking at the richness of the world, of the species, somewhere between natural history and molecular biology. I like that land. And I love the complexity it gives me.
A question about education, maybe.
Yes.
The tension between simplicity and complexity and getting to see the beauty in complexity suggested that learning to appreciate art and learning to appreciate science at a very early stage would complement each other.
Yes. Though human beings, it seems to be in nature of human beings to take complexity in varying doses. There's no guarantee that someone who is able to accept complexity in either physics or chemistry is naturally going to take to the complexity of contemporary classical music, or that they would take to abstract art movements early on. So that the complexity, but I think teaching certainly, well, I'm a little worried. I think we see time and time again a certain reaching after simplicity by young people. And that is true for moral judgments as well as for science. Golding's book, The Lord of the Flies, is a text about that. To see, looks like coming to terms with complexity in our lives comes a little with age, though some people rigidify with age also into extreme positions. But in that sense, let me just quote to get out of myself. In Primo Levi's The Periodic Table, a wonderful chemical masterpiece, he doesn't want to call it an autobiography, a selective autobiography. He calls it a history of the elements. But anyway, at some point when he's in this chemical college in Torino, and he's taken the first course, and then he all of a sudden, and then he goes over to work with a physicist, an astrophysicist who has been identified. But at that point he says that I grew tired of chemistry. Where were the theorems of chemistry? So he was looking for something simpler, more mathematical. Somehow mathematics gives that to young people. So that seems to be the way in. How they go beyond that is sometimes a mystery. How they get out of admiring the mathematics and the simplicity of mathematics, and sometimes, and how they go beyond that to go to physics, chemistry, and biology remains to me a mystery. I think we should give it earlier. I think for sure. I think we have to adapt these things to the natural inclinations of children at a certain time. I think that, for instance, Leon Lederman's idea of teaching physics first is crazy. I think that doesn't match the way that the mind of the teenager works. I think the way into children in elementary and middle school, yes, you give them some chemistry and some physics, but natural history is the way in. Living organisms, looking at living organisms, collecting bugs, teach them basic scientific questions around living organisms. I think that somehow matches both an innate biophilia and something that you've noticed with kids, making lists like of 10 top hits or something like that of the sports statistics. They can memorize incredible sports statistics. So I think taking advantage of that before abstract thinking is developed is a way to hook kids into asking scientific questions.
I have a question for you. One of the things that it seems to me that you're trying to do, since you're a poet and also a chemist, is deal with the question of representation.
Yes.
For example, you show different ways that chemists use to represent the structure of molecules,
Yes.
the ball and stick, the periodic table of elements. There was a new form, I don't know what it's called, where you use these kind of, dark and light.
Yes.
You know better what it is. But also in poetry, too. Poets are trying to represent feelings in words, and it's very hard to do because very often the word goes off in its own direction, or the series of images go in a way you don't want them to go. Do you see a parallel here? Is that what you're trying to show here in these two autograph versions of the creation of a poem and the creation of the periodic table?
That's certainly representation is essential. There is a film I saw which is very useful to show to make scientists think. It was, I think, by Brooks, and it was 36 views of an enzyme, different models, ball and stick, space filling and such. It was like 30 views of Fuji, but in another way. And it's very useful to build a bridge between sciences and humanities, for scientists to realize that while, if they are realists, and as most of them are, and there are interesting reasons why chemists are more likely to be naive realists than maybe other people. It has to do with the transformations they do, not just that tasting the tetrodotoxin. But one has to see that there is, even if there is an underlying reality, that there are 36 ways to represent it, is a useful bridge then to representation problems in humanities and the arts, where the emotional current, there is different aspects of emotional currency in these things. There is a different role for ambiguity in these two. There are differences between art and science. But to realize that we are both in the business of representing things is a very useful starting point.
Thanks very much.
Thank you very much.